right? So let's see, extend this to N-DOF system. Okay, so we wrote down MQ double dot plus CQ dot plus KQ equals tau, where we chose tau would be minus KPQ minus KDQ dot. And then we said that KD should be equal to minus C plus 2 square root K plus KP times M for the system to be critically damped. Okay, so this is 1 DOF. Okay, now let's do this for 2 DOF. Now consider a 2 DOF system. Okay, so a 2 DOF system would look something like this: M11, M12, M21, M22, where I'm looking at a matrix instead of a scalar. K21, K12, K22, Q1, Q2 equals tau1, tau2. Okay, so there are many more things here than we had previously. Now let's do the same thing. Let's say that tau is minus kpq minus kdq dot. And what does that entail? Well, it will be something like this: kp11, kp12, kp21, kp22 times q. Here q is a vector, q1 and q2. And then we have KD11, KD12, KD21, KD22, Q1 dot, Q2 dot. Okay, so for a 1 degree of freedom system, we only had to choose one number, KD, and KP was variable. Now here it's a mess. We have to choose 8 numbers, right? So we have to basically do the same thing. Take this sub in this tau. This is tau1, tau2. So sub this in here. Once we sub that in there, we'll get an expression for uh, the system dynamics, and then we'll have to sort of use it in the form which I showed you earlier, that is, to be critically damped, there needs to be some formula and use that, but that just becomes too unwieldy. This is too unwieldy. Okay, so what we do is I'm going to show you a sort of a way that people have tackled this problem of designing a controller for a N-DOF system. And it turns out that you don't really need to choose 8 numbers. You only need to choose n numbers. So if you have an n degree of freedom system, you choose n number. 2 degree of freedom, you choose 2 numbers. And 1 degree of freedom system, we choose 1 number. So this is sort of a generalization of doing this type of control. This type of control, which I'm going to talk about next, is called control partitioning. Okay, so here's how it goes. So let's again consider a m-dimensional system, mq double dot plus c q q q dot plus gq equals tau. Okay, what we'll do is we'll choose tau in the following way. So we'll assume that we have some estimate of the mass matrix. Okay, now mass matrix is something which we can measure from the CAD file, right? It's inertia and masses, but let's say that our CAD files are wrong, and so we have some approximation of the mass matrix. So I'm just going to put m hat for the approximation. Then I'll put kp times q minus kd times q dot plus c hat, which is again the estimate for the C term plus G hat Q, okay, where M hat, C hat, G hat are estimates of M, C, and G. Okay, and of course, sometimes you will have perfect estimates, in which case we can just replace M hat with M. And now let's sub in, let's call this 1. So let's call this 1 and this 2. And let's sub in 2 in 1 to get MQ double dot plus CQ dot plus GQ equals M hat minus KPQ minus KDQ dot plus C hat Q dot plus G hat Q. Okay, now what I'm going to do is I'm just going to assume that M equals M hat, C equals C hat, and G equals G hat. That is, we have perfect estimation of the mass C and G term. In fact, when you do simulations, I'll show you, we can actually do this even if the mass and C and G terms are not perfectly estimated. So let's just assume that. And so we'll get MQ double dot plus, I'm going to just skip writing this thing in the bracket. It just makes it easier to do that. G equals M minus KP Q minus KD Q dot plus C plus G, right? Now, sorry, this should be CQ dot plus G. Okay, now what you see is that you can actually cancel a few things. You can cancel CQ dot on the left side with that on the right side. You can cancel G's on each side, and you can actually simplify the expression to be M. So I take this term on the left side to get M times Q double dot plus KP, let me put KD first, KD Q dot plus KPQ equal to 0. Now, since the mass matrix is not equal to 0, okay, I can say that Q double dot plus KD Q dot plus KPQ equal to 0. Okay, and now you can see that it actually is, it's in the nice form, which is basically something like this: Q1, Q2 plus something times Q1, Q2 plus something else times Q1, Q2. Okay, I intentionally did not write those terms. So what we can do is, instead of writing a full-blown of complete matrix which is fully populated, I can actually write this as KD1, 0, 0, KD2, and then same here, KP1, 0, 0, KP2. And I can do that only because I have full control and flexibility in choosing the values for these matrices. Okay, so what you see is that you've reduced this to two simple equations. One of them is plus KD1 Q1 dot plus KP1 Q1 equals 0, and the second one is Q2 double dot plus KD2 Q2 dot plus KP2 Q2. So these are simple 1D equations, right? They look very similar to the 1D equations I wrote down earlier. So we have taken a problem which is N-DOF. This is just an example showing 2DOF, but it is N-DOF in general. And we've reduced it to N equations which are linearly independent. So I can choose KD and KP1 based on the formula I wrote for 1D system. I can do the same thing for KD, KP2, and so on. So I can write, for example, KD1 equals, if you remember the formula, so let me write down the formula. So KD equals KD equals minus C plus 2 square root M K plus KP is the formula I wrote down. In this case, I can write k di, where I equals 1 to whatever you want, equals minus c. So you can see here that um, the constant term, which actually is something like this, mq double dot plus cq dot plus kq equals 0. So the constant term is the term which does not involve the system it doesn't involve the feedback controller involving kp kd. It's only the system term that is actually 0. There's no constant term. Plus 2 square root m multiplies with q double dot, and you can see that that term is simply 1. And then we have k. The k terms is the one which multiplies with q, but we see that there's no k, there's only kp times k, so that is also 0 plus k ti. In other words, sorry, this should be kpi. In other words, we have kdi equals 2 square root kpi. It's super simple. So all we need to do is, once we do the control partitioning, like the way I talked about, then you only need to set KDI equals 2 square root KPI, and the system will be critically damped. It's a very simple formula. Okay. One second, let me just one more thing and I will finish off. Okay, so last thing before I finish off, I have one more minute, is to actually use a block diagram to show this. And block diagrams are very useful because that's how you can convey the equation in a graphical manner, and so it's easy to communicate with other people. So here's a block diagram which illustrates the system. So what I'll do is I'll write the system dynamics. Okay, so that is the system dynamics. Okay, what comes out of the system dynamics is a measurement for q dot and q, which is the position velocity. Okay, we've written down the formula for torque is basically m times kpq minus kdq dot. So it's 10:50, but give me a minute and I'll finish this and we should be done. Plus g hat plus c hat q dot. Okay, so what I'll do is I'll feed in the value for c, because c hat multiplies with q dot. Then the g actually is actually a part of q, which I did not write, so I'll put a g here, g hat. That value goes in into a block like this. This one also goes in here, so it's a plus, and that plus is because of this plus. What goes into this is the input, which is the torque. So we've seen that the torque is the sum of this part, which I already wrote, and I need to write the third part. So for that part, what I need to do is okay, first I need to take this value, which is q dot, multiply it with kp. Then I have to take the q dot multiplied with kd, and then we have q, which multiplies with kp, and these have to be fed so we have here kd times q dot, kp times q, and they are fed to, well, you need to sum them up first. So the summing block is always a circle. And once they're summed up, you have to multiply with m hat. And once you multiply with m hat, it gets fed back to this. Okay, it's not the best way of writing this. Let me put this here so it looks much cleaner. Okay. Then the m is here, m hat. Okay, so this is kpq, kdq, and m hat. And so when this is summed, this term, we circle this part, and then this part comes from here, and then the last part is sitting right here. Okay, so when you sum them up, you get that. Sometimes they also show this part, which is of a signal, which in this case is 0. It's basically the reference. Okay, so this is where we left off last time. We looked at a system which looks much like a manipulator. So that's the equation dynamics of the system. We wrote down the torque, which is using the control partitioning, which is a clever way of writing the equation such that the feedback control is simplified to choosing a single gain, right? A single gain for each of the lines on that equation. So each degree of freedom will have a single KD and a KP. KD is the derivative gain, KP is the proportional gain. Okay, and then based on this equation, I drew a free body, a block diagram, which is how people communicate. And I realized that I made a mistake here in terms of this. So here C is okay. C multiplies with C takes is multiplied with Q dot. So that's right. The G is okay. It needs information of Q. Kp times Q is also okay. Kd times Q dot is okay. However, you can see there's a minus sign. So I need to have a minus here and a minus there. And so when this minus, so what happens here in this block is right here. Let me write that A. In block A, if you see, it's basically Kp times Q, Kd times Q dot, because Kp there's a subtraction there. So I just need to put that and then the negative for Kd. And this is coming at A, and then it's getting multiplied with M. And so that's at A. Over here, if you write this as B, this instant, then B is going to be the mass matrix multiplied by Kp, Kd, Q dot. And then at C, or the torque, is really summation of, it's a summation of C times Q dot, G times, well, G is a function of Q, and then this part in B, right? So M kpq minus kdq dot, which is basically the same expression here, and that's how you interpret a block diagram. Okay, now this is for the set point. So this is for set point equal to 0, right? Set point is really not here, and when it's not here, it's really actually it's buried in here, it's actually 0. So how do you change this command to control the system to go to a set point? By set point, I mean, let's say the system is at 0, 0, 0, depending how many joints are there, and you want it to go to, say, 0.1, 0.2, 0.3 for the different DOFs. So those are the set points. So imagine a pendulum going from 0 to 30 degrees and so on. So how do you change that? Well, so let me write that down. It's actually a simple modification of that formula. Set point control. Okay, again, the system dynamics are simply mq double dot plus c q dot plus g of q equals tau. And then if you want to do the control using control partitioning, then it's tau equals the estimate of mass minus kp times q minus qd, where q is the desired or the reference, minus kd q dot plus c estimate q dot plus g estimate q. So only change is right here. This is the set point. Okay, and so you can redraw the diagram. The only difference in that diagram from the previous one is that right here we had a 0. You would get QD over here, and that's all the change will take place in the in the block diagram for this particular system. Okay, so I'll write here, just draw the block diagram yourself. Okay, and I said it's just very simple modification of the previous one. Okay, now let's do an example in MATLAB. Okay, I just cooked up a system which has no physical meaning, um, and the system I thought about is just numbers here: 0.1, 0.1, 2 for the Q dot, and then there is the damping term or C term 0.2000 0.1 times Q1 dot Q2 dot. Then the constant, the G term will have 5, 1, 1, 10. By the way, this doesn't have to be symmetric. I took them to be symmetric, but really that's not required. Q1, Q2, and then of course tau 1, tau 2. So very clearly, this is your mass matrix or M, this is C, this is G. And let's say that I want to have my set point as 0.5 and 0.1. So that's where I want the system to go. And it starts off with Qi is 0, 0. So this is the initial state. Okay, so I'm going to go from this state 0, 0 to 0 0.5 to 0.1, and I can specify a time. Really, the time is really immaterial here because I'm just trying to go from 0 to QD in the fastest possible time. And the way I do the fastest possible time is to use a critically damped system, right, with control partitioning. So let's see how to implement this in MATLAB. Okay, by the way, maybe I should just mention here in MATLAB, what I'll do is I'll essentially do m hat minus kp q minus qd minus qd q dot, and then plus g hat q plus c hat times q dot. That's precisely what I'm going to do in MATLAB. Okay, so here is the files which I'll share with you. There is basically a main file, and then there is the right-hand side, which basically takes in which basically does actually both the controls as well as the dynamics. I'll show that to you in a bit, but here is the mass matrix, which is what I wrote, the C matrix, the K, actually this is the G matrix, so same as G, same as G. I wrote here K. I didn't quite realize that I should have done that anyway. So here is, I'm going to do two cases. One is the case where we have perfect estimate of the mass matrix. So M hat is simply M, and C hat is C, and K hat is K. And then I'll show you what happens if the model is imperfect. So what I do is I start off with, well, what I essentially have here is the critically damped system. So you can see Kp is simply a diagonal matrix. It looks like this: 0, 1, 0, 0, 1, right? That's the diag. So diag equal 1, 1 is simply that. It's an identity matrix here. So if you have diag 5, 5, it will be 5 and 5 on the diagonal elements. And then the KD is simply 2 square root of KP, which is the critically damped case. Okay. Set points, as I said, is 0.5 and 0.1. And I start the system at 0, 0, which is shown here. The state as well as the position of the velocity is 0. And let me just run this first. Okay, what you see here is a plot of Q1 and Q2. Remember that Q1 had to go to 0.5 and Q2 had to go to 0.1, which they do in about, let's say, 6 seconds. Okay. Okay, so before I ramp up the gains to show you what happens, the dynamics of the system are sitting in the right-hand side. Here we have the torque, which comes from control partitioning. And then I also have q dot, which is the system dynamics, right? So I take tau, I put it in here, and that's how I get q double dot, which is the system dynamics, which I get by inverting the mass matrix and so on. So again, remember that we saw that the response to get to 0.5 and 0.1 is about 6 seconds. Let me now ramp up the gains. So 1, let's make it 10. Okay, so this is the response now with a gain of 10. And you see that it's going to 0.5, 0.1 in about 2 seconds. And I can keep ramping it up. So here it is in less than 1 second. So you can see that the effect of increasing the gain is to actually to make the system respond fast. Let me go back to 1 and now change the system, the controller. What I'm going to do is I'm going to assume that I do not have a perfect estimate of the mass matrix, the C term and the K term. So I'm just going to add some random values to the elements of M, C, and K. And now let me run this for the same gain 1 for the first case. And so if you look at it now, you'll see that when I want it to be at 0.5, it's actually overshooting, right? It's not being regulated. That's because, first of all, my estimate for the system dynamics is imperfect. Second is that the gain is not doing much. Let me now ramp up the gain to 10. And now if you look at this, you'll see that there is actually a steady state error. This is the error. So it's not perfectly at 0.1. It's slightly off from 0.5 here, but it is actually going towards the constant value pretty fast in about 2 seconds. So I can just keep ramping this up to 100. Let's see what we get. And now you can see it's much better. It's actually following pretty well. The response is also within 1 second. So this is, here is a perfect example of why we want to do feedback control. That is, our estimates for the system dynamics are imperfect, and by putting a high enough gain, the system is being regulated to the value we care about. Okay. Okay, I'm going to stop sharing, and we'll go to a physical example of a pendulum. So the pendulum which I derived actually was something like this. It was the horizontal position is actually the position from which I measure the angle. So theta is going to be the angle from the horizontal, and gravity is downwards. And I believe I think I didn't do this. I did not assume a point mass. Instead, I assumed a bar, and I assumed that the mass is here. M is here. This is the length of 1 meter. And the goal is to get the pendulum to go from 0 pendulum go from 0 radians, which is the position I've shown it, to pi divided by 2 radians in shortest amount of time. Okay, and so the system dynamics of the pendulum will be something like this. Okay, now they're very simple in this, but I'm just putting it in the general form. M Q Q double dot plus C Q Q dot plus G of Q equals tau. So that's the dynamics. Okay, now for the control, I'm going to show you the naive way of controlling this. The naive way of controlling this is to say that I'm going to put a torque which is Kp times Q minus Q desired minus Kd Q dot. So this is a simple proportional derivative control, right? This is something which you've done in Coppelius sim before. You put a P gain and you put a D gain, and this is pretty much what you did. You said you put a set point. So that's one. The second one is to use control partitioning, which means that I'll put it'll be M Kp Q minus Qd minus kd q dot plus c q q dot. Sorry, I'm missing a q dot here. Dot plus g of q. Okay, so this is control partitioning. Okay, now let's see what happens for either of these controllers in MATLAB. Okay, I'm going to show you both these examples in MATLAB. I programmed them to do both PD control as well as control partitioning. Okay, and hopefully you'll be convinced after seeing that control partitioning approach is way superior than using a simple PD control. Control file, the right hand side, and then the main file. So the RHS file is simply, what it's simply doing is it's basically finding the dynamics of the system. It just encodes the dynamics. There is a torque needed for the system to proceed further, and the torque comes from the control file. So the control file basically does a simple PD controls. You can see KP, simple PD control, a proportional derivative control, where torque is tau is minus Kp q minus qd minus kd into q dot. That's pretty much what this is doing. Okay, so with this we can run the one link main file. Again, as I said, I need to go from 0 to pi by 2, and I have to choose a proportional gain and a derivative gain. So I just chose 100 and 0.1 of kp's, or in other words, it's about 10, right? So remember, this is what we did for our pendulum example, where we tried to put a kp and kd, and we just tuned them based on the response, and that's pretty good. Let me run this now. You can see that the pendulum is actually overshot and then went back to 0. And if you look at the response, on the left side, you see the position as a function of time. You can see that there's an overshoot. I'm trying to go to 1.57, which is pi divided by 2, and then it settles down. And then here you can see that there's the velocity, the big jump, and then obviously because the pendulum has to shoot up, and then the velocity settles to 0. But that transient is something which we don't desire, right? And so we can actually try tuning this up. So when I was doing this with students, we were just ramping up gains and seeing what happened. And so we can do the same thing here. That looked like it shot much more than the previous example. So here is the shoot. It's about 2. It went from 1.57 to 2, which is not desirable. That's when you want to increase the gain. So let's make that to 50. You can see now it's much better. There's no overshoot. And then it stopped. So let me close this. The torque, this is the velocity. But look at the position. You can see that it's going from 0 all the way to 1.57. There's no overshoot, and it's settling in about 1.6 seconds. Okay, that's something you want to remember. 1.6 seconds, and I got it fairly easy by just tuning numbers 2 or 3 times. But if you have a more complex system, more than one link, then it's clearly hard to do this tuning manually. So now let's close this and open up the next file, which does control partitioning. Okay, same files, one link main, one link RHS, and control. Okay, one link main. So this file is doing exactly the same thing as the previous file, except that now I have to set KP and KD, which is based on control partitioning. The one link RHS is the same. I wrote it in slightly different form, where I wrote M, C1, G1. And then the control is based on control partitioning. Here I have control partitioning. So the torque is M times Kp q minus qd minus kd q dot plus c plus g. And that's precisely what I've written down here. Okay, And now let's see what happens. So let me just first, maybe let's start with 100 because that's what we started in the previous example. So run this. Okay, it stopped. Let's close this. On this. Okay, so here is the velocity, which is not so interesting as the position. And for position, you see that previously the best we could do with the PD control was 1.6 seconds. We got to about 1.57. Here we've actually gone down to zero point 0.6 seconds, and we had to do almost zero tuning to get this, right? The only parameter we changed was Kp. Now we can actually make this go much faster than zero point 0.6 or zero point 0.7, I would say, by just ramping up this Kp. Right, we'll make it 200, and then the KD is 2 square root of KP, and run it. Okay, it stopped. That's the torque, that's the velocity, and here's the position. It's about a little less than 0.6. So you can just keep ramping this up, as I said, and get it to go much faster and faster. So here is a gain of 1000. Okay, clearly, if you increase the gain, you're going to see a more higher velocity, higher torque. But that's what you have to do if you want it to go much faster. And you can see it's less than 0.4, it's about 0.3 seconds. So really, control partitioning is a very simple way of tuning a controller. Very little hand tuning is required, and that's sort of a principled way of doing it. Okay, any questions? I'll stop with that. Um, and I'll do trajectory tracking in just a bit. But any questions so far?